In this video, we're going to go over some different types of line integrals, which are going to be fairly important in some of the applications upcoming in Chapter 5. At the onset here, we're not going to have good understanding of what exactly these new types of line integrals are going to be good for, but at least we can define them so when they do occur, we're ready to use them. Here's at least the starting idea. Let's suppose that we were to go back to the line integrals that we had talked about in the previous videos, and maybe we replace that delta SI with a delta xi. Maybe instead of breaking up the curve C into little bits of arc length, we broke it up just into x directional changes. Well, this would then allow us to obtain a line integral of f along C, but with respect to x. Ultimately, we would get something that just looks like the following. This integral here isn't necessarily any easier to calculate because we still have a big mixture of variables. But again, we should be able to see that the only thing we've really changed about the previous definitions that we were working with is that we were going to put a delta xi at the back. Now, if we were to do the same thing, but instead replace that delta si with a delta yi, then we could get a line integral of f along C, but with respect to y. And that would look like this. Again, it's not an easy integral to calculate because we still have some messy variables sitting in there. But this is how we would define it. This will then allow us to say that, well, we might want to try to specify what was the integral that we were working with previously. And so previously, I would say we were working with a line integral that was being calculated with respect to arc length. When it had a ds at the back, it was with respect to arc length. Now, when we take a look down here at the next fact, we'll see something kind of interesting. If C is a smooth curve and we have a nice parameterization for that particular curve, and f is continuous on some region containing C, then I can always make the following conclusion. I can always state that the integral, the line integral with respect to x, can always be equal to an integral from a to b. I'm going to replace again x and y with their t formulas from the r of t function, and I'll have x prime of t dt at the back. We'll see where this comes from in just a second. I'll also be able to say that if I had the exact same thing, but with dy, I would get an integral from a to b, my function with the pieces for x and y substituted in, and then a y prime t dt. So this is kind of a strange update. What this is giving us is an ability to compute one of these integrals with respect to x or with respect to y, as opposed to when we were computing it with respect to arc length. With respect to arc length, we didn't have just a simple derivative at the back. We had like the magnitude of the r prime, we had a big square root back there, but this actually seems like it's a little bit simpler. Now, the idea here isn't maybe too surprising. And we'll see in some of the sections to come just exactly where this idea actually comes from. I'll state down here that we can note that the above definition in fact extends easily to 3 dimensions. If you can imagine, we would have the same sort of thing where we'd integrate with respect to z. As I state, it's very difficult to give physical interpretations of what these integrals mean, but we'll do that more in the next section. So what I want to take a look at here is just a little bit of notation and then example to help illustrate the point that we're dealing with here. So here's the notation. Oftentimes, line integrals with respect to x and with respect to y will occur together. This will happen all the time for us. And when this happens, it's very customary to abbreviate the following. So you'll notice here that I have a line integral with some formula dx over c. And then I have another one, but it's with respect to y, maybe a different function. And so it becomes very, very customary to do something kind of strange and write all of this input stuff all at once inside one integral. And I don't notice there have both differentials at the back. I kind of just have them next to the function that they're supposed to be working with. So this is an abbreviation of what we have, but it's an extremely common abbreviation. In fact, if you look at example 3 here, you'll see the abbreviation in use. I want to evaluate this line integral where c is the line segment from -5, -3 to 0, 2. So again, I'm going to go ahead and highlight a couple things here. First, I can see that I'm using this abbreviation from up above. I kind of can see that my p of xy function is this y squared. This q function is this x, and everything's been kind of written together. And if I wanted to, I could of course break it back apart. I don't necessarily need to, but I could. So I'll go ahead, and the next thing that I'll do is I just like to have a little visual sometimes of what exactly I'm working with. I'm working with integrating as I move across this little line segment. So I'm going to go from -5, -3, all the way up to 0, 2. So this is the line segment that I'm moving on, okay? And I want to go ahead and I want to think here carefully about how in the world can I start to make this calculation? Well, again, one of the things that I can try to do is try to create a parameterization of the line. So that's super simple. So we need to parameterize C. Okay, so how about we go ahead and let r prime of t equal the following. So this is kind of tricky. I might want to try to think here about, well, I could do a couple things here. I could try to find the equation of this line first, and then quickly just convert it over. Or I could go ahead and think also about how I could construct the equation of a line from vectors that we did even back in chapter 2, or even chapter 1. So here I'll go back and take a look quickly at how I could maybe determine that. I could see very, very quickly that I can kind of imagine that I have a starting point down here at -5, -3, and I'm going to go and move upward to 0, 2. So because of this, I can imagine that I have a starting point in R0 of -5, -3, and I can imagine that I have a direction vector to get to my next point where I have to go over 5 units and up 5 units. And with this, I could easily create the equation because I have a nice little line. So it seems like what I would do is I would start at -5 in the x, I would add 5t. And I would start at -3 in the y, and I would add 5t. Boom, I have the parameterization of the line. Okay. So you could also do the exact same thing when you, or if you were to find the equation of that green line. That's also totally fine if you were to just do that with regular algebra. The other thing we have to do here, though, is kind of define where exactly my values of t are allowed to start and stop. Well, again here, if I'm imagining that I started from position 0, I would have to say, how big does t have to get in order to get to the point 0, 2? Well, if you play around with some values, you might be able to determine that that's the value of 1. Notice if you plug 1 in for t, you're going to get 0, 2. So this is a nice parameterization. And now I can go ahead and easily think about evaluating the integral that I have up above. So here's what I can do. I can say that the integral y squared dx plus x dy can really be thought of as an integral of a y squared dx plus the integral of an x dy. I can imagine separating them back out and just calculating each of them separately. Okay, so let's see. If I was to substitute everything in here, I know that I'm going to have integrals that go from 0 to 1. If I take my y component and I square it, it's going to look like this. Although to replace that dx, I'm going to have to actually again include what we have on the previous page. To replace dx, I'm going to have to say, well, the derivative of x with respect to t is equal to 5. So that gives me that dx is equal to 5 dt. And so that's what I'm going to use to replace that dx. I can try to do the exact same thing when I take a look at the next integral. The next integral is also going to integrate from 0 to 1. I'm going to replace what x is, which is negative 5 plus 5t. But since this is dy, I will say that dy dt is also equal to 5. And that gives me that dy is equal to 5 dt. So I'll put 5 dt over here. If I can now just evaluate these integrals, I'm good to go. Now I'll leave it to you to do the full evaluation, but I'm going to point out that one thing that you'll notice is that aren't these both integrals with the same bounds? So isn't it actually totally possible that if I wanted to, I could actually rewrite these as a one single combined integral? Now I'll leave it to you to verify that if you did write this as one single combined integral, I think that you would end up with the following. Again, it'll be your job to double check me on this, but I believe that this is what you would end up with. Now you don't have to combine these first, you could evaluate them separately. But oftentimes what we'll tend to do is to kind of skip directly from this equal sign down to this one. Or sometimes even skip directly from the original problem down to this equal sign, since we can think about these as just one integral from the start. Okay. Again, I'd hit pause on the video right now to try to go ahead and see what your final answer comes up as here. All right, if you actually went through and did your calculation, here's the answer that I got. I got an answer of negative 5/6. So again, we don't really know exactly what this value might represent here, but we know that we can compute this line integral in the following way. One interesting question that we would begin to ask is, would our answer in the above example have changed if we had found a parameterization from 0, 2 to negative 5, 3? Notice that we kind of thought about a starting position where we started at the bottom and moved to the top. Would it have changed had we reversed the order of this direction? We'll take a look at that in the next video.